Combinatorics is an amazing area of math. I love it. I love solving combinatorics problems because they involve beautiful lines of reasoning. And one of the themes within combinatorics is what I call transformations of counting problems. And what this means is that if you need to count something and that exercise is hard, you can actually transform that problem into a different kind of counting problem. You can try and count something else which will give you the answer to the original problem. And in this video, I'm going to talk about some examples of beautiful transformations of counting problems in that sense. So let's get started with our very first problem, which is this problem here that says on a 4 by 5 grid like the one you see here, a person has to travel from the bottom left point A to the top right point B. He can only move one step at a time, either towards the north or towards the east, and one possible path he can take is shown. So you can see here that from point A, the person goes north, east, north, east, east, north, east, north, east, like this. And now the question is asking us, the problem is how many distinct paths exist from A to B. So that's what we have to count. How many distinct paths exist from A to B? And then the second part is a generalization. How does the answer change for an M cross N grid? So how do you think we should do this? If you want, you can actually pause the video here and take a stab at this on your own before you go forward. So what we're going to do is we are going to transform this counting problem into a different counting problem which is much easier to solve and which will give us the answer to the original problem. So the way we will do that is we will think about how to describe each possible path in a way that then makes it easy for us to count the number of paths. So here's what we'll do. For each of the steps the person takes, we will either denote it by, let's say, N, which means north, or E, which means east. So let's take a look at this specific path here. So the person goes north, then east, then north, then east, then east, then north, then east, then north, then east. So if I now have to describe this path to somebody who is not able to see this picture, I can actually describe the path just as a simple string of letters N and E. And what will that be? So that will be N, E, N, E, E, N, E, N, E. So this string of letters perfectly describes the path that is shown in this picture. And by the way, that will be true for every possible path. So let's take some other path that the person could take. So let's say the person goes like this, then goes like this, then this, then this, then this. How would you describe this path as a string of letters? So you would say east, east, so east, east, then north, then east, east, okay, so EE, then north again, then east again, and then north, north. All right. So what this really means is that every path possible can be described as a string of letters with some N's and some E's. But how many N's and how many E's? Well, we must have 4 N's because between A and B, the vertical or the north-south distance is 4 units. So we must have 4 N's always. Like in this case, we have this N, this N, this N, and this N. So we will always have 4 N's. And how many E's will we have? We will always have 5 E's because the horizontal distance between A and B is 5 units. So every string that describes a path will be a sequence of letters, 9 letters long with 4 N's and 5 E's. And all we need to do to count the number of paths is simply to count the number of permutations of these strings. So we have 9 letters in total, of which 4 are of one kind, 4 are N's, and 5 are of another kind, 5 are E's. So the total number of permutations will simply be 9 factorial by, there are 4 N's, so 4 factorial, and there are 5 E's, so 5 factorial, and this immediately gives us the number of all possible paths. So see how we transformed the original problem into a different counting problem. Instead of counting the number of paths, we counted the number of permutations of this string. So this is what I mean when I say this is a beautiful transformation from one problem to another. Now the generalization is very easy. We have to generalize this to an m cross n grid. I will not solve it fully. I will leave this to you as an exercise, and I want you to share the answer in the comments. But the idea is the same. In an m cross n grid, every path can be described as a sequence of letters with some n's and some e's. You have to think about how many n's, how many e's, what is the total length of the string, and therefore how many permutations there will be, and that will give you the number of paths. Now we'll go to problem number 2. 12 persons are sitting in a row. In how many ways can we select 4 persons out of this group such that no two are sitting adjacent in the row? So let me help you visualize this problem a little bit better. So 12 persons are sitting in a row. So I'm just going to use these circles to represent persons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 persons in a row. And what we need to do is select 4 of these 12 such that no two of them are sitting adjacent in the row. So for example, if I select this person, and let's say this person and this person, that is a valid selection because no two of these 4 are sitting adjacent in the row. But on the other hand, if I select, let's say, this one, this person, this person, this person, and this person, now this is not a valid selection because these 2 people I have selected, they are sitting adjacent in the row. So I have to count the number of valid selections, the number of ways in which I can select 4 people such that no 2 are sitting adjacent. Now once again, this is a beautiful transformation problem where to count this, you count something else, and to figure what that is, you could actually pause the video here and take a stab at it on your own before you see how I do it. So what I'm going to do is I'm going to describe every valid selection as a sequence of letters. So let's take this first valid selection over here that I marked out earlier. So what does this really say? It says that the first person is not selected, the second one is selected, the third one is not selected, the fourth one is selected, and so on. So let's just transform this selection into a string of letters. So I'll use n for not selected, and I will use s for selected. So n, s, n, s, then n, 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 so 3 n's. Then we have an s here, then an n, then s, and then 2 n's. All right. So now this gives me a valid selection. Let's take another valid selection. Let me take, I'll use a different color. Let me take this one, and perhaps this one and this one. So how do I represent this selection as a string of letters? So I will have n, n, s. So n, n, s, and then I will have n, n, s again. So n, n, s, and then I will have n, 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 s. So n, 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 s, and then n, s. So this is another valid selection. So you can see how every valid selection can be written as a string of letters which has 8 n's and 4 s's. So 8 n's because 8 people are not selected, and 4 s's because 4 people are selected. But the caveat is, the key is that none of these 4 s's should be adjacent to each other. So this is what we have to count. How many permutations exist of of these strings where we have 8 n's and 4 s's, but no s's are together. For example, in this case, we have an s here, we have an s here, we have an s here, and we have an s here. None of these are adjacent. This one again, s, 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 and s. No, none of these are adjacent. So how do we count all the possible sequences where we have these 12 symbols, 8 n's, 4 s's, but the s's are not adjacent? It's actually quite straightforward. You first write out the n's. So let's write out the n's. I'll do it here. So we'll write out the n's. So 1, 2, 3, 4, 5, 6, 7, 8. So you will have 8 n's, and now you have to place the 4 s's in a way that no two of them are adjacent. So how do you do that? Well, what you do is you just think about the spaces between the n's. So how many spaces are there? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 spaces to place your s's, and you can place your s's in any 4 of the 9 spaces, because if you do it this way, you are guaranteed to ensure that no two of the s's will be adjacent. So for example, if you place an s here, an s here, and s here, and maybe one here, you get the string n n s n n s n s n n n s, and this obviously has no two s's that are adjacent. So this is what you need to do. You just need to place your 4 s's among the 9 places. So all you need to do is choose 4 of the 9 places to place your s's. And in how many ways can you do that? You can simply do that in, you have 9 choices, and out of that you have to select 4. So 9C4. So there are 9C4 ways to create such strings, and therefore the answer to the original problem is also 9C4. Once again, a beautiful transformation of some situation to a different situation that is easier to count. Now we'll do problem number 3, which is actually a really beautiful problem. It says a composition of a natural number n is a sequence of positive integers a1, a2, a3 up till ak, which add up to n. So for example, if you take the number 3, the compositions of 3 would be, so if you take n equal to 3, the compositions of 3 would be any sequence of positive integers that adds up to 3. So one sequence would be 3 itself. Another one could be, let's say, 2, 1. Another one could be 1, 2. And another one could be 1, 1, 1. So you have 4 possible compositions of 3. What about n equal to 4? So if you take n equal to 4, what are the possible compositions of 4? So you could have 4 itself. You could have 3, 1, or 1, 3. You could have 2, 2. So that's 4. Will you have other compositions? Yes, you would have, let's say, 1, 1, 2, 1, 2, 1, 1, 2, 1, 1, and you would also have 1, 1, 1, 1. Okay, I think I've counted all the compositions, and there are 8 compositions in total of the number 4. So the question is asking us, how many compositions exist of any natural number n? Is there a formula we can find that tells us the number of compositions? And once again, this is a beautiful transformation problem. To count the number of compositions, you can actually count something else, but to find out what that is, maybe you want to pause the video here and take a stab at it yourself before you see how I do it. All right, so let's get into the solution now. So to understand what we need to count here, or what transformation is possible here, once again, let's take a concrete example. Let's take n equal to 5, and we will count all the compositions of 5 in a very elegant way. So what we'll do is, first write, because the number is 5, we will write 5 ones like this. And then we have these spaces between the ones, and there are a total of 4 spaces, and we will just place plus signs in some of those spaces. So for example, if I place a plus sign over here and over here, this actually gives me a certain composition, and what that composition is actually 1, because I have a 1 here. Then I have a 3 here because I have no plus signs in between here. So I'll think of this as a 3, this one is a 1, and this one again is a 1. So this is the composition 1, 3, 1. Now let's take another example. Once again, let's write 5 ones, and now we have 4 spaces between the ones, and we will just place plus signs in some of those spaces. So let me put a plus sign here, and perhaps a plus sign here, and maybe a plus sign here as well. And now this gives me the composition 2, 1, 1, 1. Great. So I'm generating compositions by doing this specific action of writing all the ones and placing plus signs between them. Let's take yet another example. So again 5 ones, and this time I'll not place a plus sign anywhere at all. I'll choose to not place a plus sign in any of the 4 places. So this will simply give me the composition that's 5. That's just the single term 5. So in this manner, I can generate all possible compositions of 5 just by choosing where to place my plus signs or where not to place them. Every time I do it, I get a different compositions. So all I need to do is to find out the number of ways I can place plus signs in these places, in these spaces. And how many spaces are there? So there are 1, 2, 3, 4 spaces, 4 places between the 5 ones. And for every place, I have to decide whether I place a 1 or not. So I have 2 choices for every place. I have 2 choices for this, 2 for this, 2 for this, and 2 for this. So my total number of choices will be 2 into 2 into 2 into 2. That's 2 to the power 4. And if I now generalize this result and take any natural number n, the logic is the same. To count the number of compositions of n, we just first write out n ones like this, and then between these n ones we get how many places between the n ones? We get n minus 1 places. Just like with 5 ones we got 4 places, with n ones we will get n minus 1 places, and for each one of those places we have to decide whether to place a plus sign or not. And therefore for each place we have 2 choices, so we'll have 2 into 2 into 2 up till n minus 1. So that's 2 to the n minus 1. So this will be the number of ways to place plus signs, and therefore this will be the number of compositions. And you can check that this indeed works for n equal to 3. If you plug in 3 here, you get 2 to the 2, that's 4. If you plug in n equal to 4 here, you get 2 to the 3, that's 8, which is the explicit count we got when we listed out all the compositions. So the answer is 2 to the n minus 1. Once again, a beautiful example of transforming some counting problem into a different counting problem that's far easier to solve. Okay, now we are on to our last problem in this video, which says, and this one I find this to be the most elegant of all. This one says, find the number of non-negative integer solutions to this equation x1 plus x2 plus x3 equal to 8. This is a specific equation, and then we have a generalization here where instead of 3 variables we have n variables adding up to r, and we have to find the number of non-negative integer solutions to each equation. So in this case, for example, one possible solution could be 2, 3, 3, because 2 plus 3 plus 3 is 8. Another possible solution could be 3, 4, 1. A third possible solution could be 4, 0, 4, because remember 0 can also be a value of the variable because we need non-negative. So 0 is a valid value. So how do we count all of these solutions? So let's list out some specific solutions of this first equation and see if there is an easy way to count them. So for example, if we take the solution 3, 1 and 4, can we transform it into a string of some kind that then makes our counting job easier? Let's come to this in a minute. Let's take another solution like 4, 2, 2, and let's take a third one, let's say 5, 0 and 3, and each of these 3 solutions I will try and transform into a string that makes a counting job easier. So this first one here, I will write this as, because it's 314, I'll write this as 111, and then I'll leave a space, and then I have this one here, so I write a 1 here like this, and then I have this 4 here, so I will write 4 ones like this, okay? And then what I'll do is I'll insert 2 plus signs like this, okay? So now I have this string representing the specific solution 3, 1, 4. Let's do the same thing for 4, 2, 2. So 4 to 2, I will first write 4 ones like this, then a space, then 2 ones, then a space, then 2 ones, and then I will insert 2 plus signs like this, and this gives me the specific solution 4, 2, 2. So you see what's going on here. Let's do it once more with 5, 0, 3. So what I'll do is I'll place 5 ones first. So 5 ones, and then I have a 0. So let's see how to do that, how to handle that. And then I have 3. So 3 ones like this. And then what I'll do is place 2 plus signs like this, and this gives me the specific solution 5, 0 because there's nothing between the two plus signs. So that's the 0. And then we have the 3 ones here. So every solution I was able to transform into a string. And what is the string? The string has, each of these strings has 8 ones because on the right side we have 8. So 8 ones and 2 plus signs. 2 plus signs. Why 2 plus signs? Because there are 3 variables. Because there are 3 variables, the 2 plus signs, they allow us to partition the sequence of ones into 3 parts. So in this case, for example, here, here, and here. So that's the 3 variables. In this case, we have nothing between the 2 plus signs, so that's 0. So in every string, we will have 2 plus signs and we will have 8 ones. So to count these solutions, we can instead count the permutations of these strings. We have 8 ones, we have 2 plus signs, so we have 10 symbols in total. So 10 factorial by, there are 8 ones which are all identical, so 8 factorial, and there are 2 plus signs, so 2 factorial, and that is our answer. I think this is a very, very elegant line of reasoning, and if you did not fully appreciate it, you should actually go back a little bit and watch through this again to fully understand what happened here. Just by transforming every solution into a different representation, our counting job became a lot easier. Now, generalizing this is very easy. Instead of 3 variables, we have n variables. So how many plus signs will we have? We will have n minus 1 plus signs, and they're all adding up to r. So we will have r ones because we have r on the right side. So to count the number of solutions to this equation, all we need to do is to find the number of permutations of a string which has r ones and n minus 1 plus signs, and you can do that on your own. I want you to work it out and share your answer in the comments. So that's it. That is this whole theme of transforming one counting problem into a different counting problem that makes our job a lot easier. I find this theme to be a very fascinating, beautiful part of combinatorics. I hope you liked it too. Thank you for watching and let me know what you think in the comments.